Hi everyone, welcome to another IRIS-HEP topical meeting. Today we have two presentations from Diana HEP Fellows. With a quick introduction, here's Mike Sokoloff.
So Diana HEP is in some sense one of the precursors of IRIS-HEP, and the Diana Fellows program this past summer supported, I think, 7 undergraduates who worked full-time on software projects related to high energy physics. And so today, I guess we're going to have Emile Savard first, and then Parker. Is that right? Parker Watts?
Yep, that's right. That's the schedule.
And their advisors were, or mentors were, so Daniel Campora and Tom Bocher, and from LHCB, and then Parker's was Juliet Alemena, and so you'll hear about that later.
First up, we have Emile Savard, who was mentored by Tom. Tom, do you want to say a few words to introduce Emile's work?
Sure. So Emile was working with us this summer on a problem that I think was very ambitious for an undergrad for a few reasons, because it was, one, very difficult, and two, something that his mentors had not fully figured out how to accomplish, and three, is very important for the LHCB collaboration. So we set Emile to working on figuring out how to optimize the Allen package, which is the LHCB HLT1 on GPUs. It's a software trigger fully implemented on GPUs. We set Emile to figuring out how to optimize Allen for AMD GPUs, which is very important because if we want to purchase GPUs and use them in our experiment, we need to be able to have a competitive tender process. So this is really high impact work. And so we set Emile to working on learning how to profile an AMD GPU and then optimize Allen using the information he found. And I think he came up with some really nice results that I'll show you today.
Thank you, Tom. Emile, whenever you're ready.
Optimizing Allen Backend with AMD HIP by me, Emile Savard, and then as mentioned, both of my mentors were Daniel and Tom. So as a quick overview from my Diana fellowship over the summer, as Tom was saying, I was basically working as a part of the Allen initiative, which was based on upgrading LHCB by using GPUs and by extension, parallelizing the code. But specifically, we were targeting AMD's HIP language, since we were trying to work with AMD GPUs, and AMD GPUs, surprisingly, or sadly, I should say, only use HIP. And specifically, our end goal was also, as Tom mentioned, to try to increase AMD's throughput, which was the rate of events per second, to a similar level as NVIDIA's GPUs. And as a quick overview of GPUs before I go any farther, since I will be talking about them a lot, I just want to define 3 quick terms. The first are kernels, which are just functions that run on the GPU. The second are threads, which are the workers that are allocated to each of the kernels. And the last is block dimensions, which is basically just a logical group of threads that share memory. So the idea with this, to remember, is that changing the block dimensions changes the amount of threads they hold, which by extension also changes, of course, the amount of threads that each kernel can have. So specifically, the first thing I was doing was profiling using RockProf, which was AMD HIP's profiler. And profiling code is just, running a command to collect data, and then it basically brings it into a digestible format for us to look at. So specifically in this case, it was using the hardware counters on the GPUs and recording back the results. And as you see here from, this is an example of a profile of a very small run of Allen. We have the kernel names over here, the names of each of the kernels. We have the amount of times they were called. In this case, it was only once, but in a bigger run of Allen, it will be 1,000 plus times. We have the total time in nanoseconds that the kernel ran for, the average time that the kernel ran for, and then the last, which is also quite important, is the percentage of the total runtime that the kernel took. And with this information, I was able to find the slowest kernels, and I was tasked with changing the block dimensions of the slowest kernels first to see if we could find a more optimal block dimension size. And one specific thing I thought this really taught me was the importance of resource management, and I would like to use the example of the kernel if create tracks, extend tracks. So in the top right, we have a graph of the block dimension size of the kernel by the total throughput of the program, where higher is better since we want bigger throughput. And then on the bottom two graphs, we have the block dimension size by the kernel time, where lower is better, and the same with the block dimension size by the total seconds runtime of the code, where lower is better as well. And one specific thing I would like to bring up is around the 300 mark for the kernel time, where if you see there is a very big increase in the kernel time, and this goes into the idea of resource management, since this goes to show that, if you allocate way too many resources, in this case of threads, to one kernel, you can literally just bloat the thread. So, causing it to take longer to run, which decreases the throughput, which is bad, and also increases the amount of seconds that it takes for the code to run, which is bad. And one other specific thing, though, that I think was very interesting with resource management is if you see here on the block dimension by throughput, that from the first point to about 100, the throughput increases, but at those exact same points and the kernel time stays relatively the same. So I thought this was also a very good use of resource management and like a learning moment, since it showed me that though allocating resources to a kernel may not affect the kernel directly, as in the kernel time doesn't change that much, but it still affects the total amount of resources that there are for the system. So it still does affect the system overall. And you can't just look at a kernel time. You have to have a bigger picture when you're doing something like this. And one other kernel I would like to mention is muon add chords crossing maps, which is the kernel that I ended up trying to optimize later on. And this was the easiest fix that happened throughout the whole summer, actually, was this right here, where the base block dimension size of this kernel was set to 256, which if you see right here on the graph of block dimension by throughput is quite low, which is bad. And something way smaller, like for example, 64, has a higher throughput. And this actually makes sense if you look at the code, since this parallelized for loop only runs up to muon constants end stations times regions times quarters, which we are able to find out is just 4 times 4 times 4. So this for loop never runs more than 64 times in the first place. So giving it anything over 64, like its set size of 256, is just bloating the software basically a little bit as well, and just slowing it down since it's unnecessary. And then going into the code itself, our first possible optimization spot that we were looking at was right here, where in the for loop, we calculate a start index, a mid index, and then an end index. And then we check if the start index is not equal to end index. And if that holds true, then we start doing stuff with the data. So our idea was, before the for loop, to basically calculate the start index and the end index, just those two, and see if they don't equal each other. And if they don't, then we put them to a shared array where we can index on later on, where we can index through later on. So we already have an array of all the values we want to look at. And the idea is that this would hopefully lower the amount of calculations we need to do overall as a whole. And one specific thing as well I would like to bring up with this is learning how to code for GPUs. So for example, shared memory, which is something that you can only do on like HIP or CUDA, because you don't have access to shared memory like this on CPUs. It's only on GPUs. Using things like the thread IDs and making specific threads do specific things, using functions like sync threads, which, as the name suggests, sync up the threads. And also, I learned how to use really important functions when it comes to parallelizing, like atomic add. Since a problem with threads is if you run threads, you have a chance that two different threads will access the same variable at the same time, and they will basically overwrite each other and cause an output that is inaccurate. So functions like atomic add basically just make sure that the kernels take that each kernel takes a turn in increasing a variable to stop variables from overlapping with each other. Sorry, stop threads from overlapping with each other. And then the second spot in the code that we looked at was later on, there is this function of get layout X and get layout Y, where if you look at it, is actually a pointer to another file called muon tables, and it's a function muon tables. And if we look at the function in muon tables itself, all it does actually is it's just a pointer to an array that is then indexed by a calculated value. So what I did instead was I made 4 shared arrays in muon add chords crossing maps, and I essentially just pulled all of the data of the 4 arrays that we look through in muon tables and just set them to the shared arrays in muon add chords crossing maps, so that later on, when we want to get the values from those tables, instead of having to consistently pull from muon tables, the idea is for it to be a little faster of just pulling from shared memory in the code. And all we have to do is just find we just have to recalculate an index value and then just index the shared arrays by that value. And then sadly at that point, that's when the summer came to an end and school started up again. But as an overall recap again, I learned how to profile code. I was able to understand resource management better by changing and testing block dimension sizes. I made attempts to parallelize and speed up the code. And though I did not mention it in the presentation, I think one other very important aspect is I was able to understand and build off an existing project that already had many files made and what seemed like millions of lines of code. Right? Thank you.
Thank you, Emile. Any questions? Gordon?
Yeah, really nice talk, and sounds, Emile, like a bunch of work and also pretty interesting. I wanted to ask, when you were looking at these particular optimizations, or what was causing you to need to do these optimizations, do you think they're generalizable issues? So I guess what I'm trying to say, and I apologize for not having a well-formed question here, are these lessons that can be generalized, and then other people who are tackling this can learn to follow a similar solution? I realize you didn't get all the way through, but nonetheless, or maybe an automated tool could be used to analyze and thus add or implement these sorts of solutions for the optimization?
I truthfully don't really know how to answer that question.
No worries.
Let me see if I can ask a related but more specific question. So you rewrote some of the Allen code, if I understand correctly, so that the hip back end would work more efficiently.
Yes, that was the idea.
So do you know if anyone tried taking your improvement, which made the hip back end run faster, to see if the CUDA back end would run faster?
I do not know if any of the changes have been implemented yet.
Okay, because I'm guessing that a lot of the stuff that, not a lot, but at least some of the stuff that would improve the hip back end would also improve a CUDA back end, because the logic was unrelated to the particular architecture. It was really
yes.
the whole
I
idea.
agree with that.
And kernels, right?
Mhm.
Mike, I can answer that. And we did implement, for example, the changes in block dimensions that Emile tested, and they do. You're right. They do also improve the CUDA backend.
Fantastic. So you've improved the throughput for Alan for the CUDA implementation that's been selected.
Yes.
So you've improved our trigger.
A little bit, but yes, I could say probably that I've improved it a little bit.
You know, if each of 10 people can make a 1% improvement,
It's
that
10%.
is a really big deal.
Yeah.
Thank you, Emile. Up next is Parker. Parker was mentored by Juliet. Juliet, do you want to say a few words to introduce Parker's work?
Yeah, sure. So hi, I'm Juliet Alamena. I'm a CERN fellow, and I was working with Parker Watts this summer. And Parker is regularly, he's now a senior at the University of Texas at Dallas. And this summer, we were working on a project in the context of CMS. So this is for the upgrade of CMS. One subdetector we'll have for the high luminosity LHC is the HGCal, the high granularity calorimeter. And I'm really interested in looking for new particles beyond the standard model, and in particular for long-lived particles. So Parker was working on a trigger, a level 1 trigger, using the high granularity calorimeter to look for long-lived particles. So this is work that I started a little while ago, and now Parker was working hard to optimize it for getting closer and closer to the real running conditions for the HGCal at the high luminosity LHC. So Parker will tell you more about all of that. So Parker, I think whenever you're ready, go for it.
Great. Okay, I'm going to talk about optimizing a fast convolutional neural network for identifying long-lived particles in the CMS high granularity calorimeter. So I'm Parker. I'm continuing the work of Juliet, Yutaro, and Jan. And I'll get started. It works. Okay, so I'm just going to explain some background here because I used a lot of words in the title. So the CMS is the compact muon solenoid, a detector at the Large Hadron Collider. It's a general purpose detector designed to observe new physics. So I've got a picture of that here. The HGCal is a planned upgrade of this detector. So on the bottom right, you can see prototype sensors for this upgrade. And it's designed to give good performance in the end caps when the LHC is upgraded. And the upgrade of the LHC is the high luminosity Large Hadron Collider, which is going to increase the luminosity by a factor of 10. And that's proportional to the number of collisions per time. That's why that's important. And that's going to be operational from the end of 2027. So long-lived particles, and I refer to them as LLPs in this slideshow. LLPs can decay far from the proton-proton collision point in the collider, in the detector. And there are some long-lived particles you know about, like protons and electrons, but there are also LLPs that arise in theories beyond the standard model. And some of those theories are supersymmetry and elementary particle nature, explanations of the elementary particle nature of dark matter, and triggers that assume decays that are close to the proton-proton interaction point may miss these long-lived particles. So that's the motivation for this project. And then I'm just going to briefly explain triggers because that's important in this. It's not feasible to record every event that happens. There's like 40 megahertz. So, and also most of these events aren't interesting because they're low momentum QCD. So triggers rapidly decide what information to keep using algorithms like kinematic constraints and energy requirements and things. And at the bottom, I've got a graphic of the trigger system, the CMS, which is important because what I've implemented, or not implemented yet, but the project is focused on this level 1 trigger. and that reduces the event rate from 40 megahertz to 100 kilohertz. So now I'll talk about the triggers for the long-lived particles. Long-lived particles can have distinct signatures. You can see several different ones in this picture on the right. LLP searches span a wide variety of signatures, models, and lifetimes, masses, decay locations. And oftentimes they aren't covered by the standard reconstruction or triggers. So if we don't trigger on it, then it's lost, which is the motivation for a dedicated trigger for LLPs. And now we get to the main part of the project, which is a CNN trigger for LLP decays in the HGCal. So that's a fast convolutional neural network to find non-pointing showers in the HGCal. CNNs are good at image recognition. So it can easily differentiate between the signature of a non-pointing shower and a pointing shower. And the non-pointing shower is a shower that can't be traced back to the proton-proton interaction point. And for this CNN, we've used photons, samples of photons, which are Monte Carlo. So, okay, so now I'll just talk about the neural network itself. So we can get this, we make this grid, which has eta phi, eta versus phi for the HGCal. And this part here, you can see wraps around. And the reason we do that is so that we don't split up a line, because we want the neural network to see the full line to be able to recognize it. And if we cut it in half, it may not do a good job. And we're considering the full HGCal in one phi slice. So in the bottom right, you see a visualization of the neural network. And each of these blocks is a layer of the neural network. And if you aren't familiar with neural networks, you can think of the input causes certain activations within the next layer, which causes certain activations within the next layer, and so on. So we have the input, which is an image like this, and then that goes to the per pixel pre-processing, and then it goes through the CNN blocks to a final classifier. And then the model tells us, was this pointing or not pointing? So the starting point was the paper results, the starting point of my project. And this is trigger rate as a function of signal efficiency. So it's like the rate we're triggering on these displaced photons, and the signal efficiency is the model getting it right. So sometimes it could say that this is non-pointing, but really it was pointing. So you can count how many times it gets the correct answer. And then these lines are like tracing over the threshold for what counts as a displaced photon. And it's good to keep in mind, this is energy, not PT. And then the conversion from energy to PT is a factor of 2 to 10 for eta between 1.5 and 3. Okay, and so here is a visualization of the neural network, which I think is cool to keep in mind if you're talking about it. Up top, you can see what I showed you earlier, which is the layers of the neural network. And I've circled in red the images you see. So what you actually see is each of these is a 30 by 100 image. And then there's 14 layers, which corresponds to the 14 layers of the HGCal. And then these cause activations in the next layer. And what's here is the last layer of the per pixel preprocessing, which has 4 filters. And then it goes through the convolutional neural networks. And these are good at picking out features of an image. So you can see that it's starting to recognize this this signature of the non-pointing photon. And then it goes through the CNNs into the final classifier where you get a number from 0 to 1. And so the model is very confident that this is a non-pointing photon, and indeed it was a non-pointing photon. So large activation in the last layer means high confidence photons non-pointing. And then I just put this next to the signature of the non-pointing photon so you can see how the neural network can recognize this sort of shape. And in contrast, here's a pointing photon, which is the background. And you don't get those activations in the convolutional layers. And the model, the final dense layer has low activation, meaning it's likely a pointing photon, and it was. So I'll just talk about my strategies to improve the neural network now. The first strategy, or one of them, was to add more max pooling layers, which decreases the number of parameters that the neural network must store and decreases the resolution of the image. It's important because this neural network needs to go at level 1, which means it needs to go on an FPGA. So it's got to be good and also fast and efficient. So decreasing parameters is good. Then I can increase the number of filters or decrease. This increases the number of parameters and increases the complexity. So it's like the convolutional neural network or the convolutional layer itself can recognize more features of the image. So you can see beneath the convolutional layer, there's one grid for every filter here. You could add and remove CNN blocks, which affects the number of parameters. Or you could change this pre-processing that I talked about, which would change the input size to the first CNN block. So here I just put a layout of several different models that I tried. So here's the original one that you saw earlier. Oops. And then here is an add block 8 filters. So what that means is I've added a CNN layer, and then I've changed the complexity of the CNN, all the CNN layers. So they are all only 8 filters now. And here 3 colors, I've reduced the number of filters in the pre-processing layer. And in this one, I've increased the complexity of all of the convolutional layers. Here, I've just removed the pre-processing, 2 of the pre-processing layers, and changed the number of filters to 3. And then here, I've both added the block and removed the pre-processing. And now I'll show you how those models did. So I plotted a bunch of them here. Something to point out, removing the pre-processing was a bad idea, but several of these did well, and the changes were ones that reduced the number of parameters. So it was promising here. And then this is also for the energy of 10 to 30 GeV. So that's only the photons in that energy range. And then now you can see all of the energy ranges. As the energy gets higher, all of these lines sort of converge, so it matters less and less. And here I've just blown off or showed the best models. And then at all energies for completeness, with the original add block in 3 colors. So now I'll talk about minimizing resources, because I talked about getting better, making the model better. So one way I did that was by pruning, which removes unused parameters in the neural network. So sometimes there's numbers you're storing that aren't doing anything for the next layer. They're not causing activations. They don't really matter. And if you could just remove that, then you could reduce the size of your neural network, which would make it smaller, which is good because it needs to go on the FPGA. And then quantization, which reduces precision of numbers that the model must store. And so the interesting thing is you can prune the model and quantize it, and then you can train the model while it knows that it's pruned and quantized. And so it figures out the best way to do those things. So here I've plotted the efficiencies of the pruned and quantized model, which did not hurt the ROC curves, which is good. Too much, at least. They're pretty close. And then here's for all energies, like before. And the final step was to look at the resource requirements with the HLS-4ML package, which is like you make the machine learning model, and then you use this package to do synthesis, which is like converting the code to what it would look like on an FPGA. And then you can print out the resource requirements to see how it perform on the FPGA, and we can see if these resource requirements are met or not. And later on the road, later down, hopefully it could be implemented. So I've just put everything in a table here. You can see the model, and I put the best models we had. And then you can see the latency on the FPGA. And this mode is part of the HLS-4ML package. So if one of those layers I talked about was too large, then the number of parameters forced the HLS-4ML package to run in resource mode rather than latency mode, which meant there were just too many parameters for like one of the calculations. So I modified another model in order to run in this latency mode, which gave a better time. And what we were shooting for is we consider the full HGCal in one phi slice, but really it will be split into 4 slices. So we could have like an FPGA for each of the 4 slices. So we divide this number by 4, and we were looking for 4 microseconds. So in this chart, we're looking for 16 microseconds. So this number came the closest, which was good news. This one is not actually plotted though. It's just a slight modification of the 3 colors pruned and quantized, where I've reduced the final CNN complexity so that the package can run it in latency mode. And it was still training before I could put the results in. So it was like a last second thing, but it looks promising. And so in summary, I've continued to work beyond the proof of concept paper by optimizing neural network models to identify non-pointing showers, and I've showed that the required latency is likely feasible when implementing the CNN onto an FPGA. And that's all. Sorry, I think that did that run a bit long. I had a lot to cover, but yeah, that's all.
No, that was fine. Thank you. Thank you, Parker. Any questions? Gordon, you have your hand raised?
Well, I mean, come on. With a last name like that, I have to. It's so rare to see somebody else with the same last name. That was a great talk, and it looks like an absolutely terrific amount of work there. So very nicely done. When you were making the initial set of adjustments, not the ones where you were trying to get everything to fit into the FPGA or working on the latency specifically, but when you were looking to understand whether or not you could improve the efficiency or the background rejection, were there some set of principles that were guiding you in those modifications, or was it more you were trying various things and seeing what what piece of spaghetti stuck to the wall, so to speak?
Yeah, it was not an algorithmic process. I think there's some sort of intuition to it, but there were some general principles about how CNNs work, how they can find the features of images that helped to guide me in that. For example, the trade-off between minimizing or of the max pooling, where you decrease the resolution of the image, so you couldn't see very fine details, but you decrease the number of parameters. So the idea that this line is not a very complex shape, that meant we could reduce the resolution by a lot
I see.
and still keep
Okay.
the idea. Yeah.
I'm very happy to hear that in some places it wasn't just shooting in the dark, that there is some well understood behaviors that were guiding you.
Yeah,
All right,
for
thank
sure.
you very
Yeah.
much, and really nice work.
Thanks.
Any other questions for Parker? Mike?
Yeah, so I am very impressed by this work, partly because I've been doing work with deep learning for several years now, and we haven't had quite the same sort of luck in things like pruning. When you did the pruning, roughly how much did you reduce the size of your model? Was it 10%, 50%, 90%?
Yeah, for the models, I told it to prune until 50%. Yeah, in the
Okay.
convolutional
And
layers. Yeah.
do you know how much that degraded the performance?
Yeah, I can show you the.
No, you don't have to show the details, just round numbers. Was it a very small, did you just take a very small hit?
Oh, yeah, it was relatively small actually. The lines in the rock plots were pretty close.
Because if you had chosen something like, if you'd chosen to prune more, could you fit into the latency budget with a small loss in performance?
Yeah, it's possible. I think the dense layers are where the pruning can really help with the efficiency. I think. I mean, with the latency. And yeah, I'd just have to try it and see. Yeah.
And then the last question, again, it relates to pruning. So I don't know if, have you read the Lucky Lottery Ticket Hypothesis paper? Are you familiar
No,
with that?
I have not.
Okay, it's you can Google it. It's a sort of a classic, but it suggests that with pruning, you should go back and with the pruned network, restart the training in an earlier point with the same parameters you used earlier, but now you're going to train the network, not where you pruned it, but you're going to retrain from an earlier stage with whatever parameters were used to get to the pruning. But since you have fewer layers, you're going to tend to improve the performance.
Okay,
It's a
interesting.
slightly
Yeah.
complicated idea, but it's one which, at least in the literature, claims that you can get better performance with smaller parameters using pruning as a key element.
Yeah, because what I did was prune the model, prune an already trained model, and then train it for several more epochs. But
right,
I think
and what they say is that if you go back to an earlier stage and you use exactly the parameters that you had found at that earlier stage, then you'll actually have a more performant algorithm. Because it looked like you want to get down to 16 microseconds and 19 is really close. So it looks like some small amount of tweaking could make this really interesting in terms of having something that can be deployed in the experiment.
Yeah, for sure.
Yeah, very impressive work. Thank you.
Thanks.
Any other questions for Parker? No. Well, thank you, Parker and Emile, for your presentation.
Maybe I guess one last question, but this is for Juliet.
Okay.
Okay.
What do you judge the outcome of this work to be?
Huge success.
Wait, does this look like something that can really be deployed with a bit more work, of course?
Yeah, I think we're getting there. So Parker is going to give a presentation at a CMS level 1 trigger meeting, and I'm curious to hear their feedback. But I mean, Parker improved the latency by an order of magnitude. I'm happy.
Okay, thank you all very much.